by thanking you for the invitation and the great hospitality. Of course, it's always great to be here. So today I will talk about the brain realization or the brain engineering of two-dimensional gauge theories with little supersymmetry, with 0,2 supersymmetry. I will explain what these things are. And this is work that I have been doing over the past year with a group of collaborators, Dogu Kim and Sang-Min Lee from Seoul University, Rak Seong from KIAS, and Daisuke Yokoyama that is now at King's College. So I will organize the talk as follows. I will first begin with some introduction, some motivation of why we want to do the kind of things that I will tell you about. I will then briefly review what are these two-dimensional 0,2 theories. Then I will go into what I really want to achieve, which is to engineer some class of these theories by putting some brain probes on some singularities and devising some T-dual brain configuration in which, it's a closer, it's a nice link between geometry and gauge theory. I will explain how these objects connect gauge theory and geometry, how they simplify this connection, and then I will tell you about a few applications. In particular, I will tell you about how this new infrared equivalence for two-dimensional 0,2 theories called triality is realized in this context, what it means, how it emerges, and I will talk a little bit about dimensional reduction, how it arises here. So, of course, we use quantum field theories, use particle physics, condensed matter physics, a wide range of areas with doing extreme calculations with high precision that are all the time tested, and it's fine. But it's fair to say that there's continuous progress in understanding quantum field theory at a fundamental level. We keep learning about things like holography, integrability, new ways of thinking about scattering, how to think about theoretical Lagrangian, or about dualities. Theories that seemingly look different, but they lead to the same physics. And engineering or realizing quantum field theories in terms of string theory or in theory in terms of brains, for example, is a powerful approach that in many of these has played a role in many of these developments. And sometimes it helps you to uncover new phenomena, or alternatively it gives you another perspective in which some things might be more obvious than others. So people who are discussing things in the blackboard over there, sometimes you get some ideas which are geometrized in terms of brains. So let me give you a prototypical example of the kind of things that I want to do today. Some of you might not be familiar, but this is some kind of program that we want to repeat. And it turns out that the following is true. So if you put these brains flowing certain type of Calabi-Yau threefold singularities, realizing the n equals to 4 theory that we were discussing before, you obtain all the work volume of the D3 brains and an infinite family of four-dimensional superconformal field theories which generically have n equals to 1 supersymmetry. And what we realized and discovered many years ago is that there's a T-dual configuration to these brains at the singularities, which we call brain tilings, which look as follows. So as some kind of, they are described by some bipartite graph. Bipartite is something that is made out of two types of atoms, such that one type of atom is already connected to the other type of atom, living on a two-dimensional torus. So here I'm marking, telling you what the unit cell of this configuration is. And so this is one configuration that we are interested in. So we are interested in looking at the quantum field theory and the rise of the work volume of the D3 brains. By T-duality, it's related to this object, which should also be thought as a brain configuration. If you want, it's a two-dimensional serialization of the kind of Hanani-Witten diagram that was drawn in the blackboard. So here, what we think is that these lines are representing an inspired brain configuration. So to an object that is heavy, which is the T-dual. So this lattice is T-dual to the Calabi-Yau-3 geometry. And on the surface of the screen, I have D5 branes now. The D3 brane has been turned into a bunch of D5 branes. And these objects are finite in these two internal dimensions. So at the end of the day, they give rise to a four-dimensional gauge theory. So what's interesting about this kind of objects is that it's very simple to read the quantum field theory from here. You can read what the fields are, what the gauge symmetry is, and what the superpotential is for this configuration. But it's also very easy to read out the geometry from here. So this is some object that is like a missing link between geometry and quantum field theory, for example. And in particular, it has simplified the connection between quantum field theory and geometry a lot, and it has found a lot of applications. By now, of course, in the context of the ADS-CFT with n equals to 1 supersymmetry was one obvious. We played a role in finding some infinite families of these examples. But, so also some very mathematical things like associating cluster algebras to Calabi-Yau-3 force to local model building of string phenomenology. If you have a control between the map between quantum field theory and geometry, you can engineer quantum field theories that you might be interested for model building, for example.
This brain tiling sort of goes all the way to infinity,
so you can think about the covering space. So that's why I drew it like that. It's like, but it just lives on a two-dimensional torus. It's a periodic time. These two directions have to do with two U1 isometries of this Calabi-Yau-3. The third one is the U1R symmetry that is not. It can be geometrized, but it doesn't appear there. Very good. So let me say a few things about two-dimensional theories with 0.2 supersymmetry, which is the subject also of today's talk. No, this is very simple, but there's no supersymmetry for the mean by 0.2. There's no supersymmetry for the left mover, and there are two supercharges for the right movers. And they're interesting for a variety of reasons. Theories of this type have appeared on the well-volume ferritic string, sound vortex, or flux tubes in four-dimensional supersymmetric gravity theories, or domain works in three-dimensional theories. So these are interesting theories, and it's timely to study now because over the past 2 to 3 years, we have seen a lot of progress, similar to the progress that we had 10 years ago or so in four-dimensional theories, on the field theory side of these fields. Now, even though you have very little supersymmetry, there's still reasonable control due to chirality, holomorphy, and anomalies. And things that that people have achieved. For example, they have related these quantum field theories in this program that is very fashionable nowadays to gauge theories in higher dimensions, or to field theories in higher dimensions. You can think about this thing as arising from, say, 6-dimensional theories compactified on some block form manifolds, or by different types of dimensional reduction from four-dimensional theories. People have studied in detail the normalization group flows. There are new methods similar to A maximization in 4 dimensions, which is called serialization. And most recently, 1 year ago or half a year ago, there's a new, people have discovered a new low energy equivalence that I will explain between quantum field theories of this type. So it's very nice results on the field theory side, so we want to develop a little bit the brain side. So, the understanding of how these two-dimensional theories are realized, in particular in terms of this kind of configuration of brain side similarities, was relatively underdeveloped. And what we want to do today is we want to realize a class of these theories by putting B1 brain probes that will support the quantum field theory, probing some Calabi-Yau-4, some similarities which is Calabi-Yau-4. So the state of the art so far was due to these people, and was only about regarding only B1 brains on Oliver, and some brain configurations that I will explain now that is called brain ghosts. So one can argue that it's something that is quite limited. So what are my goals today? well, I want to study this kind of configuration. So here I have a representation, something that looks like a cone, something that is singular. So I'm going to introduce some non-trivial structure in the quantum field theory. I want to develop the map between this geometry and the quantum field theory living here. For a class of geometries, which is this so-called toric, some special class of differential for singularities that is quite general anyhow. I want to find out whether some special structure in the quantum field theories that arise from this kind of configuration. Then I want to find the analogs of these brain tidings, which are these objects, which is somewhere in between the geometry, this kind of description, and the quantum field theory that simplify the connection between the two. And I want to exploit them in order to study the dynamics. So this is the wish list of what we would like to do, and I will go over them as we move forward with the talk.
So, in terms of the 2D field theory, what is the Calabi-Yau fourfold? How does it arise?
Yes, so the Calabi-Yau fourfold will emerge as the classical model space of the quantum field theory.
The classical?
Yeah, because as you know, in 2 dimensions,
right.
We shouldn't. Nowadays we're studying the quantum field theory, and I mean, it plays a much more important role. So as you might see, everything is pointing to the fact that this thing is flowing to some nonlinear sigma model with this guy as a target space. So this will be already suggested by the fact by how triality emerges here. Okay? But today most of the talk will be basically classical, but there are a lot of but the quantum picture fits with everything that we are going to say today. Yeah, so that's a very good question.
So I have an idea are some of these or conformative theories?
So I'm going to construct the theories, and the argument is that they flow to some interesting conformative theory in the infrared part. Yes. So line in review of 2-dimensional 0.2 theories. Well, we can talk about them in so-called 0.2 superspace, which contains 2 coordinates x0 and x1 and 2 right-handed harmonic coordinates, and there's a bunch of superfields. There are vector superfields whose only degree of freedom will be some left-handed fermion in the German representation. And there are 2, for those of you familiar with n = 1 supersymmetry for dimensions, there's some change here. You have 2 types of matter fields. One are the so-called chiral fields, which contain a scalar, counterscalar, and right-handed fermion, and the Fermi fields, which only contain the left-handed fermion. Of course, you see that these guys don't see supersymmetry. That's why they don't have a super partners there. And this theory, and that's when we become more clear in a short amount of time, have a symmetry under exchange of the Fermi fields with its conjugate. So
I'm sorry, chi is a bosonic? Is it a scalar or?
No, I mean if you write down the vector superfield, it has some gauge field, it has this guy, and it has a d term, and this is everything. Yeah, and there's also some auxiliary field in the Fermi field. So the type of theories that I will describe today are so-called can be described like quiver diagrams. So let me just, for those of you that are not familiar with what a quiver diagram is, let me just tell you what it is. So a quiver diagram is a graph which represents the gauge symmetries and matter content of your gauge theory. When you have matter, for example, that transforms into 2-index representation, like we can buy fundamentals or things like actions and so on. So every gauge group or every vector supermultiple will be represented by some node, like for me we will represent the UN gauge group, and then chiral fields will be represented by oriented arrows. An oriented arrow will mean that this object transforms under, for example, the anti-fundamental representation of the gauge group at the tail and the fundamental representation of the node at the head. And Fermi fields, I will represent them, they transform also by fundamental representations, but I will represent them by unoriented lines because of this symmetry that exchanges Fermi with the conjugate Fermi. So they don't have any obvious hierarchy.
So they're still in the fundamental of each side, or in the
Sorry?
They're still in the fundamental of each side.
Yes, so there could be actuals, and actuals are things that start and end on the same line. I will see examples of that. Yes. So every Fermi field is associated to two holomorphic functions of the chiral fields, which are called E and J. So these are holomorphic functions of the chiral fields. And they arise as follows. So the E function arises as some deformation of the chirality condition on the right hand side. So you see that the so-called E terms have the same quantum numbers of the lambdas, the same base quantum numbers of the lambdas. And the J terms arise through, introduce them or appear in this kind of coupling. So you have some Bayesian invariant coupling between lambdas and J's. So they have the conjugate quantum numbers of the lambda. So if you integrate out the auxiliary fields that are there in the Fermi fields, you will get, for example, this kind of Yukawa-like couplings between a pair of fermions and a bunch of scalars coming from the E terms and the J terms, and contributions to the scalar potentials that are proportional to these object squares. So if you look at this, and you only have seen four-dimensional n equals to 1 supersymmetry in your life before, you see that the E's and the J terms, the role that they are playing is very similar to F terms in 4 dimensions. Right? So it's like having two sets of F terms. So I don't have F terms for every field, I have only F terms coming from this Fermi field. Some people combine these things into something that is like some kind of generalized superpotential or whatever. But these are the roles that I play. And you know, if we exchange lambda and lambda bar, what we have to do is we have to exchange the role of E's and J's. That's the symmetry I was talking about. So, okay, so what did we do? So we are interested in these two-dimensional theories from toric area of force singularity. So what we did first is, we work out some systematic procedure for deriving these two-dimensional gauge series for our arbitrary toric Calabi-Yau force. Toric here means that it has some, it can be thought as some torus vibration over some base space. So this is some geometry that has some, in this case U1 to the 4th isometry at least. So this is the question that we're interested in. We're interested in some, let's say, maybe complicated geometry, and we want to determine what the quantum field theory is. And what we're going to do is we're going to do the following. We are going to consider a simple geometry for which we can determine the quantum field theory. Let's say, for example, an orbifold of C4. And we are going to pick it such that we can obtain the geometry we are interested in by so-called partial resolution, which is some smoothing of the geometry. This kind of toric area forces are described by some diagrams of this type, which are called toric diagrams. They are three-dimensional, polytopes with integer points. It doesn't matter what it means. It's a picture of the geometry. So if I give you one of these diagrams, I'm telling you what the geometry looks like. In particular, C4 would be some tetrahedron at the corner of this diagram, and refinements of that diagram correspond to orbifold. So if you look at this, it looks like a refined tetrahedron. It's something like a C4 more some CK, CK prime, CK double prime, where the order of the orbifold group has to do with how long this thing is in each direction, and of course you can have different orbifold actions and a different looking diagram. So partial resolution corresponds to eliminating pieces of the diagram. So this would be an object that could be obtained by smoothing this diagram. The quantum field theory on this side is simple. It's obtained by the usual orbifolding procedure. If you want, you add images under the orbifold group of your original theory, and then you project onto things that are invariant. And obtaining a simple quantum field theory is obtained by, let's say, this operation corresponds to some Higgs mechanism. In the same sense of the same thing that I say about the moduli space. This is a theory generating procedure at this point. Yes.
In orbifold, for two-dimensional field theories, we also expect that it's not just modding out, but also adding in twisted sectors.
Yeah, that's
mechanically. So that. Okay, so that's also included.
Yeah, yes, I'm including the usually.
Just with naive, I mean, just to keep you understand, so you could have like 4 Ds, but you need to preserve supersymmetry. Why do you have 3? You have one phase for each. You have C4, so you have 4 complex coordinates.
Yeah, I think that this is the most general thing that you can have.
Or you can rotate each of the 4, but you want to preserve supersymmetry.
Yeah, you have to preserve supersymmetry. It imposes a condition on
one
it.
fix.
Yes,
Okay.
C4.
Is it true that every solid Calabi-Yau form is not used by this partial resolution?
If you start, it's everyone can be obtained as a partial resolution of a complicated thing. There's a more interesting part of the story that in 4 dimensions you start seeing behavior that you don't see in 3 dimensions, which is, for example, there are things that don't have so-called pre-part resolution. And this is something for which these gauge theories are also interesting, because you can study this non-pre-part resolution. And it's something that you don't see for Calabi-Yau 3, which is that the resolution is not Calabi-Yau. So, using this kind of roadmap, we survey the landscape of the quantum field theories that arise from this in this context. So let me show you a set of examples of how they are related that we study. It's probably not so visible, but you see things. So these lines correspond to partial resolutions, and for all these theories we determine the gauge theories. You have several guys that look like corners. This one. So these are different orbifolds of C4. You have C4 here. You have other things that look like a 2-dimensional object with an initial point. These are Calabi-Yau 3 force time complex plane. And then you have this one and this one. And then you have objects that are neither orbifolds nor Calabi-Yau 3 force time sig that are sitting in the middle. So this is the whole picture. So now we are very let's say you have ways of obtaining these theories, you have alternative ways of obtaining these theories and these theories, and everything makes like a consistent picture. So, for example, this one here, if you the conifold is Calabi-Yau 3 we like a lot, and its Story diagram it's a square, and this guy is like a square which represents conifold times C. So this theory, you can obtain it by dimensional reduction of the Klebanov-Witten theory. So this is a theory that in fact doesn't have 0.2 supersymmetry, it has 2.2 supersymmetry. And every vector multiplied in 4 dimensions descends to a vector and an adjoint chiral here. Then every chiral goes down to a chiral plus a Fermi, and you can also write the E and J terms here. And there are other things, like these 2 guys, which are not orbifolds or not dimensional reductions. We give them a name, it doesn't matter the name. So these are the quivers, and we have also determined the E's and J's, but I'm not writing them here. I mean, if I tell you this part of the story, I'm not telling you what the quantum field theory is. I'm not fully specifying what it is. So the bottom line is that
So in this language, if you know how to do a partial resolution, you know what that operation is on the quiver diagram?
Yes. Now that's I'm not telling you that, but there's a systematic way of doing it. And what I'm going to do is we're going to do something that's much more efficient than this. So this is what we were doing in order to to survey the set of these theories. Already it's not telling that, even though I'm not telling you, if you tell me this guy, I tell you which verbs exactly to turn on and so on. But yes, that's all we're doing. And you can arrive to completely generic the theory for arbitrary toric similarities in this way, in particular things that are not only false or things that are dimensional reactions.
Non-crapped similarities, does that mean when you resolve them, you get something that's not Calabi-Yau, so is the condition for specificity more general than having Calabi-Yau fourfold?
Yes, you will see. I mean, and even here you cannot even think about them in terms of this. Well, you can already see them at the level of these diagrams, for example. So these are guys. The simplest example is the sum C2 for already. That's one of the C2 for depending on the action. That is not already non-Krepan resolution. It has a non-Krepan resolution. And you might imagine that, well, you look at it, I'm not showing it to you, and you see that there are problems when you start removing this object.
Problems, so you expect supersymmetry breaking? Or
No.
Just that you'll go outside.
Yes, and the geometric description of these special guys, well, the field theory has additional objects that allow you to do the equivalent of the resolution. It allows you to do that. So that whenever this happens, these objects are supplemented by additional points that allows you to do that without breaking supersymmetry. So, okay, so we did that. I'm not telling you what the story is, but let me just say that all these examples are not generic two-dimensional 0,2 theories. All these lines that come from this kind of Calabi-Yau manifold have some special additional structure. So to constrain it, but it's still something that is there. And it has some special structure of J and E terms that are called toric structure. And what happens is that every Fermi field participates in 2 J terms and in 2 E terms. So this is example of the conifoil. So here I have the 4 Fermis, which are these for these lambdas here. You have 4 of them, and you see for each of them I have 2 J terms, which are the guys that have the conjugate quantum numbers of these fields. So these are the nodes under which this thing is charged. You can think about them as matrices. And I have 2 E terms. And if you look at this, these are just the F terms of, in this case, this came from dimensional reduction. These are the F terms that come from Riemann-Witten superpotential. And this is a simple combination of the corresponding bifundamental and the actions that appear when dimensional reducing. More generally, it's much more general than that, but it's still true that every Fermi gives rise to 2 of these guys. Now this is crucial. If you give me this quiver, I can cook up like many gauge invariant combinations of these objects, and all these things are, in principle, allowed terms. It turns out that these precise guys are the ones that give rise to the right geometry, or the rise from the geometry. It's the same thing in 4 dimensional equals to 1, that it's not the arbitrary superpotential, that you have very special superpotentials. And furthermore, this structure having 2 terms is something that will allow a very combinatorial description of this quantum physics and analysis of the quantum physics. Okay, so let me just draw this thing more for generic theory. Generic theory, things will look like this. So this is some Fermi field lambda ij, and there will be some j term that couples to this thing. So I can represent it by some kind of a plaquette. I can close the loop by the lambda field. And there's another one for the Fermi field, and there are 2 other things. There are 2 other loops of chiral fields, some holomorphic function of chiral fields that close with lambda conjugate. So these are the terms. So that's it. So every quiver will be of this type. So we can kind of put them together and think about some object like that, that for the time being is just a nice graphical representation.
So you're saying this is a constraint on the purpose, they have to only have those kind of
Yes.
4 plaquettes.
Exactly. So the ones that come from this kind of geometries are of this type. In general, it's not too same, but for these particular geometries, you can solve like that. So this makes us introduce something that we call periodic quiver. By some object that is very similar to the one that we had in 4 dimensions for Calabi-Yau 3-4. I told you that the quiver only contains information about the matter content and gauge interactions, and I have to supplement it with E and J terms. But this object is a quiver, but that on top of that will contain also the information about the E and J terms in a graphical way. So it's something that not only specifies the matter content, has this thing built in, and it will look like this. This is a complicated example, it doesn't matter. So if you see, I have numbered the gauge groups 1 to 8, so you see that the 8 is already repeated, so this is something, it's called periodical because it lives on a 3-dimensional torus. The fact that it lives on a 3-dimensional torus is it's encoding the fact that these series have a U1 cube of this global symmetry coming from the isometries of the underlying geometry, and in this kind of representation, the interactions are given by the minimal plaquettes. So they will become even easier to read from the dual object to this graph, but at this point, we believe that these things are in there. So at this point, it's just a rephrasing of the quantum field theory information. We are going to use it in some useful way briefly. And this is the statement about the global symmetry. So what is our goal? Well, our goal is now we engineer these quantum field theories, this Calabi-Yau 4. We have a way of obtaining them systematically. Now let me construct this T-dual object, which was so useful. The analog guy was so useful for studying formation of quantum field theories. So let me construct the corresponding object. So let me go back to the original days of where the only thing that people discussed were orbifores or C4. In those days, these authors, in 1955 and 6 and like that, and 687, introduced what so-called brain box models. And brain box models are as follows. Now it's a realization of some kind of Hanani-Witten configuration. The gauge theory will be, there are some V4 brains, which extend along these directions. And then there are 3 types of Lebesgue fibrils, which are orthogonal to each other. And how many you have depends on the ranks of the orbifold. First of all the brains share 2 dimensions. This is the 2 dimensions in which the quantum field theory lives. Then there are 3 directions that are compactified on a torus. This is already similar to what I was mentioning to you before. And all of them sit at a point in the complex plane made out of 8 and 9. And our symmetry corresponds to rotation in this direction. And brain box model looks something like this. You have boxes, you have V4 brains sitting there, which are the analogs of the brain interval that you have on the blackboard. And depending on the orbifold action, it's how you stack these brain boxes on T3. For example, if you have a brain, one of these boxes adjacent to itself due to the periodicity, it will mean that, for example, anything that stretches between this thing and its image is an action case, so it will be, for example, that you didn't orbifold that given direction of this direction. And this work already came with a dictionary. which was already written in the language of the periodic quivers that I was talking about, said, well, whenever you have a box like this, so think about a piece of a periodic quiver like this. Periodic quiver that contains the gauge group, and then it has 4 chiral multiplets and 3 Fermis. If you think about it, these are, this is, if it was only this gauge group, this would be the periodic quiver or the quiver for C4, which is the dimensional reaction of n equals to 4 superjumblings. So in n equals to 4 superjumblings, you have 3 chiral multiplets, which gives rise to 3 of these chirals plus a Fermi, plus 3 Fermis, and then you have a 4th one that will come from the vector multiplet.
Really a stupid question, but these lattices can become a higher dimensional theory, like in this dimensional deconstruction.
Well, you can imagine that, in some limit along the Higgs branch, these things could be something like that. Actually, when people deconstructed like the 6-dimensional theories in this paper by Nima and Karch, they looked at the periodic quiver that corresponds to the orbifolds on.
Yeah, I think that's also how the right lattice gauge theory is like more than equal 4, but in each point it's just a matrix, no? When you put many and you get the lattice gauge theory.
But so what people do is, in that case in particular, I know they use the periodic quiver. Yes. But it wasn't a periodic quiver for a 2-dimensional theory. And as I said, the orbifold action is determined by periodic identification simplification. So what's the status of these things? Well, at least these brain boxes, first of all, you can think about this thing as some bookkeeping device. It's not telling you much more than, when you have orbifolds, you have these kind of objects that you have to read about this thing, about it in this way. Of course, you can see already that chiral fields are treated in a not very democratic way. This diagonal guy is different from these two guys, at least from the point of view of this configuration. At the same time, you can think that these objects also give you like an idea of what the physical brains that you should consider here are, but not much more than that. And in particular, they are not objects that are not really related to the geometry. Any questions so far? So now what we want to do is to generalize this thing in order to introduce some object, some configuration that more or less involves the same kind of ingredients, but that on top of that captures the geometry in a better way. And that's what we want to do. And we want to do it for arbitrary Calabi-Yau force singularity, not just orbifold. So the configuration will look, it's actually very similar to that. What happens is the following: you have D4 brain, again along the same directions, and now these 3 types of S5 brains are replaced by an S5 brain that is wrapped in some holomorphic surface in this 6 directions. So the way you read it is precisely the same. You can think about the previous configuration as some disintegration limit of this kind of construction. So the gauge theory lives in the 2 common directions to the brains. Then there are 3 directions which are compactified on the torus, and you want asymmetries also. Rotations of the plane transfer to the brains. So it's very natural to combine these 6 directions into complex coordinates in a way that 2, 4, and 6 are the arguments of the complex direction, so they are periodic. And this sigma is actually dictated by this object. So this is how the geometry makes it into this construction. It's given by the holomorphic surface, which is defined by the vanishing of this polynomial. And this polynomial in 3 complex variables has coefficients for each of these points in the lattice that defines the geometry. You know, every NS5 brane, at least when you think about it in terms of plane box models, but now it's, well, more generally, the entire NS5 brane on sigma generically breaks on 1/8 of the supersymmetry. Of course, there are non-generic configurations which don't break all the supersymmetry, and then the uniform branes break an additional 1/2. Okay, so I'm not going to draw all these Riemann surfaces for you, but the non-trivial, or most of the non-trivial information about the gauge theory is captured by some tropical limit of this surface. I mean, you can think about tropical limit at some skeleton of the surface. And that would call that a brane-bit model, and brane-bit model fully encodes the two-dimensional gauge theory in the sense that it gives you the quiver and the E and J terms, meaning some object which is dual to the periodic quiver. So this is the same quiver I was writing before for this only force of C4. I slightly rotated to make it easier to dualize, and the dual object is something that is made out of this octahedron, truncated octahedron, something like that. So again, we read it in the same way that we read the other configuration. Now we think about the integers of this object as containing stacks of different branes. This entire structure is the skeleton of the NS5 brane, and the way you read it is every brick, every ball here in this case is a gauge group. They're oriented at unoriented faces, and there's a prescription for determining them. That corresponds to, oriented corresponds to chiral fields, and oriented corresponds to Fermi fields. Very good. And the edges here correspond to E, so one contribution to the E or J terms. So far at this point we are not doing anything, we're just representing things graphically. So, as I said, every edge is one of these plaquettes that corresponds to one monomial in the E's and J terms. You can also see that these Fermis are squares, and they could be chiral squares, but the Fermis are always squares because they involve 2J and 2 E terms. So now we have this three-dimensional graphical representation, which at this point is not very clear what it's useful for, but let me explain to you that it's a very nice bridge between the gauge theory and the geometry. Okay, that it allows, for example, one of the things that it allows you to do is to determine these quantum field theories directly instead of finding a more complicated theory and then resolving. So, and it simplifies the connection in the two directions. It allows you to go from geometry to field theory and from field theory to geometry. So let me tell you how to go from geometry to field theory. So the way you do is you have to read the toric diagram as follows. Every external edge here of the toric diagram, this toric diagram for C4, will give rise to a surface on this three-dimensional torus, which we call a phase boundary, that is basically normal to the edge. By normal I mean that the winding numbers on T3 are going to be controlled by the difference of these two points. And this is a generalization of some construction of Buffer and collaborators that they did similar things for Calabi-Gauss 3 force. But here it's slightly more complicated. So let me just say one thing. So sigma was defined by this kind of action. And I told you, so these are three complex variables, and I told you that the directions of the T3 corresponds to the arguments of these three complex numbers. This is a so-called coaviva projection of this sigma. This is a complex four-dimensional, two complex dimensional object which is difficult to visualize, so you can think about projections of that. One of the projections is in terms of the arguments, and these edges represent directions along which you can send the absolute values of these guys to infinity in some particular way. There's one, let's say, leg for each of these edges. Once you do that, once you go to infinity along this direction, which is some limit of sigma, this polynomial becomes dominated by just two terms, which are these two terms. So it simplifies to something like that. And you know, if you think about what happens,
But usually there is some restriction on the polynomial for the to be Calabi-Yau, right?
yeah. So this is, I mean, originally it could be a four-dimensional object. Yeah. The fact that it's three-dimensional is already it's Calabi-Yau here,
Okay.
and you know, it's convex and things like that. So you see that you get a surface whose winding numbers are controlled by the difference of these objects. So if you think this is C4, so there are 6 of these edges, and they correspond to some surface. Well, here I don't know. There was also the T3, but you know, they wind in different ways around T3. So this guy is a diagonal. It winds precisely. It's like normal to this object. So it winds a number of times. The same for the yellow, the orange, and so on. So the statement is that you can, if you give me this geometry, you can construct this object, and you can reverse engineering the quiver that corresponds to that. And it goes as follows. So the chiral and Fermi fields arrive at point intersections between these phase boundaries. And there are two types of intersections that give rise to this matter field, which are something that is called an oriented intersection. And you know, to every edge you can associate an orientation on the plane, on the phase boundary. For example, by picking the combination of the two normals. This is a canonical way of doing it. Now it's something that is pointing outwards of the toric diagram. So if you add these two fields, you will get something that points upward. And so here I show some intersection between the corresponding three phase boundaries. And if you look at it, the intersection, around the intersection, looks locally like some combination of polyhedral cones. And there will be two of them which will be special, which are guys for which the orientation is either all the planes are pointing inward or outward of the intersection. The other cones are not like that. So you can, whenever you have this thing, you're going to put the chiral field along these two cones, and you put the gauge group there. There are other guys which are some other special type of cones and biarized which are not oriented, but are alternating. And for example, let me look at the intersection of these four guys. It's very difficult to see, I apologize, but if you look at these two particular cones, you will see that the orientation alternates on the edges between going and going and going and going and going and going. So this is what gives rise to the Fermi. So this construction is true for any orbifold, and it's preserved by partial resolution, so it's true. Of course, there might be some more physical origin of these things. In the case of the Calabi-Yau three-folds, was obtained by doing an additional trigonometry which is mirror symmetry. So I'm pretty sure that there will be an additional plane construction of this thing. But at this point, it's something that is true, and you can show it's true. So with this algorithm, you can go ahead and given geometry, construct the corresponding gauge theory. You have all the entire information. So for C3 or for some C4, some orbifold of C4, you have, for example, in this case, these 6 objects. You have different types of intersections, which will give rise to the Fermis and the chirals of the periodic quiver that I showed you. And you can reconstruct it. And of course, this agrees very nicely with partial resolution, but it's something that already gives you the gauge theory directly from the geometry. If there's someone that has worked with, I don't know, brain tilings or maybe on-shell diagrams and reconstruct them from permutations or from 6-up paths or something like that, this would be, well, this is the 3D generalization of that procedure. So in mathematics they call it like Thurston diagrams or something like Thurston diagrams. So this would be the 3D generalization of this construction. So when NEMA tells you, you can construct an ocean diagram from permutations, you do the analog of the phase boundaries and you reconstruct it. So this is a three-dimensional version of that. So the other thing that this construction does for you is allows you to go in the opposite direction. It allows you to go from gauge theory to geometry in a simple way. As I said, the way the Calabi-Yau force flow arises here is as a more or less case of two-dimensional gauge theory, which I have to solve for vanishing J and E terms, vanishing D terms, and I have to find some nice variables that make this toric structure manifest. And that's a problem that becomes very quickly very complicated. So, however, I told you that these fields have a special structure which makes this easy to, you can do it combinatorially. So, the E terms look like this, just 2 times, the J terms look like that, and this motivates the introduction of some new type of object living in this brain-brick model, which have something that we call brick matching, and I won't tell you how it is. It has a simple combinatorial definition. It's a collection of phases on the brain-brick model. If you want, it's a collection of chiral fields and Fermi fields. With a simple description, with a simple definition, and this definition, for example, is that if the Fermi is contained, then only the chiral fields, one chiral field per plaquette of the J terms is contained, or something like that. And what this allows you to do is that it automatically solves all the E and J terms. So this is an ansatz that automatically solves all these things. So this is, when you compute these things by brute force, this is the complicated part of the story, because these are some variables that have some nice geometric properties, and you have to compute some dual code, and it becomes computationally involved at this point. So this ansatz, in which every chiral field is expressed as a product of new variables, which are these combinatorial objects that are called brick matching, raised to power 1 or 0, depending on whether this object contains the chiral field or not. This automatically solves all the F and the all the J and D terms. And you can think about them as some Bayes-Linear sigma model fields in the toric construction of this Calabi-Yau formula. And this that does for you is give you a combinatorial algorithm to obtain the geometry, and it works as follows. Given one of these brick matchings, you can associate coordinates on C3, which is the coordinates of the point in the toric diagram, by looking at just the intersections of these objects with the boundaries of the units. So let me give you like a simple example. This was the conical times C. This is the chiral field content of the different brick matchings. You already see that there are 2 guys which are contained in one of these brick matchings. So with my dictionary, I would say that phi 1 is equal to phi 2 2. So they automatically are implementing the relations that come from the E and J terms in this case. And this is an example of what happens when it's a dimensionally reduced theory. This is the extra bond here. Now, and with this you can look at very complicated geometry. So it's actually thinking in this way, given the special structure of these gauge theories coming from these geometries, allows you to develop these methods that connect geometry and quantum field theory in a simpler way. Now let me change gears a little and let me talk about triality and what happens in this context. So, as I said, 1.5 years ago or so, 2 years ago, these people found a new low energy equivalence between 2-dimensional 0,2 theories, which is reminiscent of cyber duality in 4 dimensions. And the prototypical example is something, a theory of this type, which you can call the 2-dimensional super QCD. And these square nodes are global symmetry groups with some ranks. This is a gauge symmetry, and the theory has some fundamental chiral multiplex and the fundamental chiral multiplex and some Fermi. I would call that the things that are charged under the H symmetry. I would call it the flavors. This would be the electric flavors if you want. And in addition, in order to make things more symmetric, you might at this point also introduce Fermi, which is a singlet under the H symmetry, but transforms non-trivially under the global symmetry, and introduce a J term here. And the number of colors is constrained by anomaly cancellation in terms of the ranks of these blue nodes. So what they found is that this theory at low energies is equivalent to this other theory. So again, the rank of the gauge group has changed depending on the flavors. You see that the new flavors are like some rotation of the original flavors, and very in a similar spirit to cyber duality, you can think about also giving rise to mesons, some composites of the original theory. So you can think about the combination of the chiral field and a Fermi to give some kind of a Fermi meson. Then this Fermi and this chiral cannot combine because the quantum numbers are not such that you can form a gauge invariant, and the chiral and the chiral form a chiral meson, but there was an original quadratic J term here that becomes a linear term in the new meson, which is like a mass term. So you get a Fermi chiral pair, vector pair that becomes massive, and you can integrate that. So this is how this thing arises. And one of the nice things, slightly different from duality of this operation, is that if you do it again, you don't return to the original theory. It's of order 3, it's only up to 3 realizations from the same gauge group that you return to the original theory. And you can prove this, or you can provide evidence for this equivalence in many ways, and it provides a new tool for investigating this quantum field theories that hopefully is as useful as cyber duality was for 4-dimensional n equals to 1. So now the question is whether this thing appears in any way in our construction.
So,
yes.
But you can embed this triality in a general quiver?
Okay, yes, and so the point is that triality in this context, well, has been proposed for this thing, for this super QCD. They also have a proposal of triality for some class of quivers. It's not generic class of quivers. In particular, it's a class of quivers in which basically you have these things that will give rise to mass terms whenever you need them. Okay, so in that context, in that sense, you can. So the transformations of the quiver are the usual ones, and then for the interactions you put in, and this is the class of theories that they define. What you need. So what I will tell you is triality for the class of quivers that I have, which you can think about the generalization of triality. Okay, so they have different types of interactions, but as I said, we have support of that at the same level of all these things that they computed there, both in our paper and the one to come. I will still call it triality. I don't want to steal it. It's some generalization of triality to these things with the different quivers and different interactions which are not in the class generically of the quivers that they describe.
So there was a central charge of that, so this goes to infrared.
Yeah, so you can compute the central charge and
square.
Sorry?
And square.
Yeah, I don't remember what they got for this. I don't think it's taken with square, but it might. But well, so what does it mean in our thing? Well, triality corresponds to a local move or local transformation of the main configuration, very similar to the continuation through infinite gauge coupling that you do when you Hanali-Witten or things like that. It's more general than this, but let me just describe at least on this thing So there will be gauge groups in the theories that we described. So what I want to do, I want to talk about triality transformations that keep us within the class of theories that are described by this construction. Of course, there are other things, but so one of the possibilities is you have a gauge group that corresponds to the following thing. It's a cube which has 4 chiral fields and 2 Fermi fields. And the triality corresponds to that transformation. You preserve the entire brain-bit model outside this object, and you replace the internal structure by this thing, suspended from the same brain-bit model as before. So if you see the cube is rotating, and this gives you the exchange of the original flavors for the new flavors. Remember that there was some exchange of some chirals for Fermis or chirals for chirals with the conjugate quantum numbers, and these diagonal legs, which are in general the mesonic fields. And you have all the interactions that you need, and which are these edges, and whether these guys are integrated out or not depends on the structure outside of this object. And this operation is such that one can prove that using these combinatorial techniques, that this operation preserves the Calabi-Yau manifold. So if I turn things around, you can say, well, everything that I told you was like a black box that you input Calabi-Yau manifold and it spits out a two-dimensional gauge theory. But one of the things that I wasn't telling you is that this operation is generically one-to-many, it's not one-to-one. And if you look at this non-uniqueness of the gauge theories for a given Calabi-Yau that I told you, it turns out that all of them are related by triality. The same transformation of the quiver, and some rather natural transformations of the E's and J terms.
That was more or less the story.
That was the story.
Of the toric symmetry or toric.
Yes, so that's a story for four-dimensional theories. Here it's different. Honestly, if I had classified the gauge theories for this Calabi-Yau fourfold before the paper of Gladwell, I wouldn't know how they are related. I would say that that's a new thing. If you want, this puts order into that. And when I say the cube move, so then there are differences already from four-dimensional. In 4 dimensions, there was only one type of move, the square move, which cube move is the oldest extension. There are other transformations which are possible here, and you can classify and also deliver triangle. So it's much more simple than that. And there's something that is I'm not going to say, but it's a very beautiful implementation of these transformations in terms of these phase boundaries that I told you. These surfaces from which I reconstruct the quiver, you exchange them in pairs in a way in which the intersections change orientation precisely as you need in order to produce, to change the flavors for the magnetic flavors and so on. And it's of order 3, as it should be. So in the last 5 minutes, let me tell you about something else. I mean, this is, it's a very trivial, not real application, it's some interesting visualization of things. So let me tell you a little bit about dimensional reduction. So we can obtain, if we do naive dimensional reductions of 4-dimensional equals 1 gauge series, we obtain 2-dimensional 2,2. And the dictionary that I already implicitly mentioned a couple of times goes as follows. Every vector in 4 dimensions goes to a vector and an adjacent chiral. Chiral goes to chiral Fermi pair, and the superpotential produces the J and E terms, produces the J terms the following way. We have one J term for each of these Fermis that arise here, as it's an F term, a corresponding F term, and then you get an E term, which is basically the corresponding chiral field dressed by the actions that come from the vector model. And So imagine we start from four-dimensional n-1 theories that come from the Calabi-Yau threefold. And let's try to see what the corresponding theory for D1 makes on Calabi-Yau 3 time series. So these objects were described by these two-dimensional lattices, the brane timings. So how do I reconstruct this object from this one, or this object from that one? And you know, of course I can determine this guy directly, and that's what I did many times before, but that's a simple prescription. So we call it the lifting algorithm. And it goes as follows. So imagine I start from the conifoil, from the four-dimensional theory. So here I'm going to tell you about the conifoil. If you remember, the conifoil has four gauge groups. So there's a unit cell that I'm not showing here, but has four gauge groups that go to these places. Every edge here corresponds to four-dimensional chiral multiplet, and there are two quartic couplings that's between the chiral multiplets. That's a superpotential. So the reduction goes as follows. I'm going to start from this object and generate one of these three-dimensional objects. First of all, each phase here will generate some new chiral phases. These are the adjoint chirals. They come from the vector multiplet. And furthermore, each node will give rise to helix of Fermi fields, because you get one Fermi field per each chiral. But you know, each chiral here gives rise to chiral Fermi, and you can show that, well, you can see that, you know, stretching things in this way automatically gives a helix of shade terms, and you have helix of shade terms over precisely all the ones that come from all the F terms in the dimensional reduction. So you can do this procedure and obtain a corresponding brane big model that in this case looks like this. Some more interesting things to say. You may imagine that you can do not so trivial dimensional reduction, such that you turn on something that breaks supersymmetry to 0.2, and you can argue, I know, since I'm geometrizing the global symmetries in a nice way, so this T3, you might hope that there's a way of doing this kind of more general dimensional reductions like Kutazo or Van Lier, etc. Okay, so it turns out that there's something that one can do that we're investigating right now. It works, which achieves precisely that. You know, it generates two-dimensional 0.2 theories, and it's it, which also have a geometric. So that's an additional condition, which also come from the Calabi-Yau fourfold. So it seems to be some combination of Kutazo-Van Lier with something else that preserves the geometric correspondence. That's the next study. So conclusions. So
I'm sorry, just on that. So what is the dimensional reduction that breaks it to 0, 2? You just make anti-periodic boundary conditions.
So you have to put some fluxes for some of the lower symmetries. Okay, and yes, so in this context, it looks something like this dimensional reduction, which is like these layers, plus something that looks like changing boundary conditions. Yes. And what happens is that the geometry grows up in this direction, which is controlled by this action. And there are many nice things that happen when you do that. For example, you know, there will be some combinatorics of how you change this. Well, it's some kind of a reflection, and you know, you can already see that once you do this a number of times. So it's like some dimensional reduction plus orbifolding, but it's not trivial orbifolding because it's connected to an action on the Calabi-Yau threefold. But you already see that when you hit some number of layers, you will already hit the possibility of having more than one different theory that corresponds to the same Calabi-Yau fourfold, for example. So this is an automatic way of generating reality duals in this context that we didn't have to guess, and you know, that's one thing that happens. Another thing that happens is that, you know, we were asked whether there was an analog of a 0.2 version of Klebanov-Witten, for example. There was some deformation. Of course, the dimensional reduction of Klebanov-Witten is that. I mean, the deformation by some kind of mass deformation. So with this procedure, you can educatedly find genuine 0.2 versions of that, for example. So that's something that we are doing now. But it has worked. So, conclusions, and we hope that this procedure can be put in the language of 2001 Lee, maybe with some additional breaking by Wilson lines or something like that. So we introduce these kind of configurations, which we call the leading models. We try to do one based on the similarities. They fully encode an infinite class of two-dimensional theories that arise in this context. They simplify the connection between geometry and H theory. They provide the brain realization of triality. If you want the non-uniqueness of these algorithms that I outlined for you, generate the duals. So let me just mention a few sets of future directions. Something that we are doing now is we're doing more quantum, and it turns out that the clavier geometry indeed is important. It's not just a definition of the theory. You can use it to compute the elliptic genus of these theories. The gauge theory and the geometric computation look completely different, at least to me. We agree very nicely. There's also some very nice interplay in the case in which you have abelian anomalies that I didn't discuss, but these are answered by some stringing mechanism, kind of neutral mechanism. You have these objects. This would be the field theoretic counterpart of the non-Crepant resolvable geometries. So it's a very nice interplay. In the original paper on triality, they already suggested that there might be some integral structure associated to this thing, to triality. It's related to what's called the tetrahedron equation, which is similar to the Young-Baxter equation. And if you look at how people like to think, some people like to think about this tetrahedron equation, it has to do with something like a Young-Baxter move, and that is what precisely our phase boundaries and our realization of triality in terms of these phase boundaries, this surface does. It's exactly that. Again, they show it here, but it's precisely what it does. So probably what we did is going to shed some light into this. And there have been, these are objects that, while these brain models of the Clavey graphs, these are things that are being studied a lot in mathematics. For example, in combination with cluster algebras, and people have associated already cluster algebras to some two-dimensional theories. So in the case of theories that come from brain tiles, there's a combinatorial interpretation of some of these cluster variables. So it would be interesting to see if the new objects that we introduce here, these big matches, provide some combinatorial light into cluster algebra, or if you can generalize what the cluster algebra is. Because if you look at what the cluster algebra typically defined in terms of equivalent mutation, which for us is cyber quality, reality is clear not that. So it's a natural generalization, I think. Okay. So, thank you.
So, is the content of the triality that the target, the probability you get in the end is the same, or is it more big than that?
Yeah, so it has to do with what actually, which is what we're exploring here. We are saying something about where these theories are flowing to. Okay? So, yeah. So at this level of this talk, it's just that. It's a non-uniqueness of this map between the geometry and the quantum field theory. Right? That's how it appears. But of course, we were doing many classical things here, so it will be interesting to. And this is what's working. But it's more on that.
Maybe going back to this central charge, do they become the volume of something in the
That's what one might think. We haven't computed anything.
How about the conformal manifold or the exactly marginal operators?
Yes.
They correspond to something geometrical.
Not that I know. I mean, you wrote something about these things for 4 dimensions, right?
Right.
So he wrote the thing for the analogs in 4 dimensions. So I guess there must be some generalization of that.
Okay, thank you.